Yeah, so I start the recording.
Okay.
Yeah, I think it's a good time to start. So let me briefly introduce Professor Wen. So it's my honor to invite Professor Wen to come to CMTC to give a virtual seminar. Although I think everyone knows who he is, but let me give a brief introduction. So Professor Wen got his PhD with Edward Wheaton back to 1987. And he was working on the first ring hierarchy theory at the beginning, and then he transferred to the condensed matter theory. So he then proposed a very famous like a D2 topological order, like a chiral Lagrange liquid stuff like spin liquid, and then he introduced the idea of like what's the SPD phase in 2010, and now he's going to introduce his new idea about what's the categorical symmetry and how we can use this to apply into some phase transition and more abstract stuff. Yeah, please start your talk, Professor Wen. Thanks.
Yeah, thank you very much, Yuan. And yeah, it's I'm very pleased to give this talk here. And I remember about 2 years ago, I gave my first talk about this categorical symmetry, also virtually in Maryland. And so
and Xiao-Gang,
yeah.
you may not remember it, but one of your very first talks on Cat Moody and the edge state was at Maryland also in 1990.
Wow.
That's when
Okay.
Shin told me about you. And I said, let's get him to come give a talk. And you came from Princeton and gave a talk.
Yes.
That was in 1990. Okay.
Yeah. That's a time. That was
long time ago. Yes.
And so in my last talk, I basically using very simple example to explain this notion of a categorical symmetry. But certainly there is an issue, why we need that, why this is useful. And so today I try to explain a few simple, again, not so simple example, but still quite simple. And I try to demonstrate, yeah, this categorical symmetry maybe is a useful concept, probably can produce some new results. So let's consider a one-dimensional quantum system in 1 + 1 dimensional space-time, and with S3 symmetry. Okay. So the standard thing we ask for this system is that what is a phase and a phase transition? Then according to this Ginsburg-Landau symmetry breaking theory, and we see that this S3 group have a 4 subgroup, the S3 itself, and the true subgroup Z3, Z2, and Z1. Z1 means no symmetry. And so therefore, this 4 subgroup means that there is a 4 symmetry breaking pattern. So S3 can break into this 4 symmetry. And so that corresponds to the 4 gap phase. Okay, so that's a Ginsburg-Landau theory. And also Ginsburg-Landau theory also tells us that the continuous phase transition are given by a pair of the group subgroup pairs. So like S3 and Z3 is a pair of group subgroup, and S3 and Z2 is a pair of group subgroup, and etc. So actually we have a 5 pair of a group subgroup relation, and so we have a 5 continuous phase transition. Okay, and then the continuous phase transition are described by gapless phase, we also call the critical point. So we may say, what are those critical points? In 1 dimension, we know those critical points pretty well. And for example, this Z2 symmetry breaking critical point is basically given by the Ising CFT conformal field theory. And the S3 to Z3 symmetry breaking pattern actually also break Z2 symmetry. So they are really described by the same Ising CFT, and etc. For example, this Z3 symmetry breaking give us this so-called Z3 parafermion CFT. And this S3 to Z2 transition actually is not quite same as a Z3 symmetry breaking. So it describes a similar but really different CFT. This CFT have the same central charge, but really a different CFT. So we call this a three-state pulse model CFT. Okay. Then what is this symmetry breaking pattern for the S3 to Z1? So we completely break S3. So what is this CFT? And so here using the categorical symmetry, we try to show that actually if this S3 to Z1 transition is a stable continuous transition, means a continuous transition by tuning only single parameter, then such a CFT must be the same as the S3 to Z2 CFT. So basically these two symmetry breaking pattern, although they are different, but they must be described by same CFT. It sounds very strange, is that possible? Maybe this is impossible. Then alternative is that this S3 to Z1 transition do not exist as a stable continuous transition. So either we have two different symmetry breaking pattern described by same CFT, or this S3 to Z1 just do not exist. The S3 to Z2 indeed exist, so they are numerically can show. And so this sounds very strange. So what's going on here? And so we do some numerical work using tensor network to do the 1+1 dimensional system and to get some phase diagram. So the model a little bit more complicated, so I won't describe the model Hamiltonian, but I just gave some phase diagram. So in one case, we find this kind of phase diagram, the phase diagram here. Okay, so indeed we have all four gap phase. Okay, and also have all five transition. But this transition is really from S3 to Z1 transition. It looks like we have a direct transition. But this direct transition, actually, if you look at it more carefully, it's a first order transition. Yeah, it's a first order transition. But the other four transition here, these four transition are continuous transition, is a second order transition. And then we can tune some parameters and get another global phase diagram. Here we get the transition that this is Z3 phase, this is Z2 phase. We get the direct transition between Z3 and Z2. But again, it's a first order. And that's what we expect because Z3, Z2 are incompatible symmetry. They are not group subgroup relation. So we only have first order transition, but no second order transition. And then we try to fine tune things a little bit, maybe not quite fine. We tune things a little bit more, try to go between these two cases, and we find this situation. So in this situation, it looks like at least within numerical resolution, looks like there's direct continuous transition from S3 to Z1, and also from Z2 to Z3. So this actually is maybe it's a multi-critical point. If this critical point is a multi-critical point, so it looks like there's a multi-critical point connecting S3 to Z1. Yeah. So this is kind of numerically seems that there's some suggestion like that. But we did not really do a very extensive numeric search. So we cannot say this S3 to Z1 cannot be a continuous transition. But it looks like in our limited search, we only see the first order transition, but no second order transition. So there's a possibility maybe this transition just do not exist as a continuous, stable continuous transition. And so this will be kind of a little bit of surprising results. And also, but this phase time also led to another question. So now we have a multi-critical point. So what is the CFT for this multi-critical point? What are scaling exponent and etc. And so we are also going to address this question here. Okay. So this is so basically this is like a kind of a setup, a background. So we try to using a categorical symmetry approach, try to address this question at this global phase diagram. And one thing I like to remark that it seems that the global phase diagram is pretty interesting. I didn't expect that. even for this very simple symmetry like S3 symmetry, this global phase diagram may give us surprise. So I can wonder if you pick any other symmetry group and compute the global phase diagram and to see what symmetry is possible, which transition not possible, and what is critical point. Maybe there are some interesting surprise we need to address even for this very simple problem, which is thought we understood very well.
Hey, Xiao-Gang, I'm a bit
Yeah.
confused. Can you go back to the last slide?
Yeah.
This phase diagram, global phase diagram, is purely numerical, correct?
Yeah, this is numerical.
So when you are saying it's surprise, let me think of this as an experiment, right? I mean, real experiment. And you get that, and some of these you do not expect. Is that what you're saying? I'm trying to understand what you mean by surprise.
Yeah, I expect, for example, because S3 to Z1 transition is a lambda allowed.
Yes.
So I expect by tuning some parameter, we can easily see this continuous transition. Just like this boundary, all other 4 boundaries are continuous transition.
Okay, I was going to say.
But somehow I couldn't find it.
Okay.
And I tune some other parameter, I see another boundary like it. But both these 2 boundaries are first order transition.
Yeah, okay.
And then we try again, we get this one. So somehow, so certainly we did not do a very extensive search. But it's just a suggestion. Maybe they don't exist.
Okay, I understand what you mean. Okay, good.
If they do exist, I will say that this transition critical point and this critical point will be identical. That would be quite surprising. Two different transitions have identical CFT. That would be surprise. If this is needed exist, these 2 transitions will be identical CFT.
I got it. Thank you.
That is conclusion. So I try to explain why we have this conclusion here. Yeah. So let me try to just introduce this categorical symmetry. Why we need that? And so we know that to discuss the phase and the phase transition, we need to specify the symmetry. A different symmetry gives rise to different phase and phase transition. And we also have anomalous symmetry. The certain different anomalous symmetry also give us different phase and phase transition. Well, recently we see that there's a higher symmetry and anomalous higher symmetry, and there's algebraic higher symmetry, and there's a anomalous algebraic higher symmetry, and all this more generalized symmetry appear. All those different symmetry would give rise to different phase and phase transition. So it looks like we will have a very rich, very complicated theory to describe all those situations. Okay. So actually, let me just mention that it's a so-called algebraic higher symmetry. It's also called a non-invertible symmetry or non-invertible higher symmetry, or it's called the fusion category symmetry. So basically, it's a symmetry which go beyond a group. We can no longer use a group to describe a symmetry. Okay. So all those generalized symmetry can emerge as a low energy effective symmetry. You may say that in nature, we don't have those symmetry, why we study that. But in some sense, yes, we do. When you have a quantum system with a large energy scale separation, then at the low energy subspace, we may have this generalized symmetry. And this generalized symmetry can be all this kind of weird symmetry here. Okay. So in this sense, the categorical symmetry is a unified way to describe all this symmetry using a single formalism. So that's one way to understand categorical symmetry.
I have a question. Yeah, question. So when you mention symmetry, is it like a unitary operator on some spatial slice, or is it like a defect in the space-time manifold? What's your definition for symmetry?
Yeah, that's a very good question. And so usually the symmetry is defined as some kind of transformation, which may not be unitary transformation on arcane system. So actually, all those I think all those symmetry I described here can be written as some transformation. There's a transformation. But more generally, I would say that the symmetry this is like a selection for local operator. When you have a symmetry, when you have a transformation, then there are certain set of local operator which are commute with the symmetry transformation. And so therefore this so symmetry is better to be viewed as a way to select local operators. a subset of local operator is so-called a symmetric operator. And the Hamiltonian is a sum of those local operators. And if you have a probe, which is respect symmetry, then the probe only involves correlation of those local operator or local symmetric operator. So this may be a better way to look at symmetry. And so actually I find this a very useful way. It's kind of like, in this case, we understood the categorical symmetry actually describe this local operator algebra.
Thank you.
So, so basically, this slide is kind of addressing this question. So what is categorical symmetry? Actually, there's many ways to look at the categorical symmetry. And the first time we come to this is really we realize that the symmetry can be viewed as a non-invertible gravitational anomaly. So therefore, categorical symmetry actually is a non-invertible gravitational anomaly. And then there's an easier way to understand that is using it's a symmetry plus it's a dual symmetry. And so this maybe is a more familiar way to look at it from condensable matter point of view. So we know that when you have a symmetry at a critical point, for example, we have order parameter, order operator, or disorder operator, or disorder parameter, something like that. But actually, the symmetry charge corresponds to order parameter, and the symmetry transformation correspond to disorder operator. But the dual symmetry can reflect that can switch. So the dual symmetry also have a transformation, and the dual symmetry transformation corresponds to order parameter, and the dual symmetry charge corresponds to disorder operator. So basically, every symmetry has the dual symmetry. If you view them together, or another is that if you view order operator and the disorder operator together in the combined unified fashion, then this point of view is a categorical symmetry point of view. So that's another way to look at this. And because
Xiao-Gang, hold on for a second. Now I'm a bit confused. Are you saying that categorical symmetry cannot be defined in a gravitation-free universe? Because your first thing is a non-invertible gravitational anomaly. Do you mean just mathematically say a gravitational anomaly? I'm just trying to understand the statement since I don't follow the field.
Yeah, unfortunately, this part is historical. And basically, in high-energy physics, a field theory with an anomaly or with a gravitational anomaly means that it has certain properties, have certain constraints in some sense.
Okay, so you really mean it in the anomaly sense. Okay, I understand. Okay, good.
Yeah, we don't really mean gravity.
I fully understand. It's like chiral anomaly. It's
like chiral anomaly. Yeah,
it's
the
certain
chiral anomaly
constraints.
is a gravitational anomaly.
Okay, good. It's certain mathematically well-defined constraint on the field theory. Okay.
On the field, exactly. It's a and this mathematical constraint on field theory is equivalent to a symmetry constraint. I
understand, but it's very well defined what it is. Yeah.
Both are well defined for quantum system indeed. But we know that the gravitational anomaly is related to the topological order in one higher dimension, and so therefore we can also view categorical symmetry as a topological order in one higher dimension. So this became a holographic point of view, which is very useful. And so today I will basically discussing these two.
Okay, so let me understand what you said, because I certainly under the statement topological order in one higher dimension. So you are saying the gravitational anomaly, the first line, is really equivalent to topological order in one higher dimension. If I take the holographic view, right? That's what you're saying.
Yeah, that's a one.
And I understand what you're saying. Okay.
Yeah, that's a one-to-one correspondence. Okay. Yes. And so basically the data to describe the gravitational anomaly and the data to describe topological order in one higher dimension is the same data. But this one I try to say that the data to describe symmetry and data to describe gravitational anomaly also very closely related, are almost the same data. And certainly the topological order in one higher dimension, this topological order, their quasi-particle described by so-called the braid fusion category. So therefore topological order and the braid fusion category also related. And the last point of view is just mentioned. We should view symmetry as an algebra of local symmetric operators. Okay, so therefore, this equivalent class of algebra of local symmetric operator is describing a symmetry, and this equivalent class is also categorical symmetry. And looks like this definition and the previous definition are unrelated, but actually, yes. And in the recent paper, we show that in this local operator algebra, there are extended operator. And then the extended operator define a rediffusion category. So these two are very close related. So it turns out all these point of view are close related. So give us a kind of maybe a more, I try to say a better way to look at the symmetry. And at least for me, I find this way is very convenient, at least unify all those different symmetry and non-symmetry in the same framework. They all can describe by this framework. Okay. So let's concentrate on this the first point of view, the second point of view, and the third point of view, and try to explain via example what is symmetry and the dual symmetry. And the symmetry and the dual symmetry can be described by using the conservation of their corresponding charges. Okay, so let's consider 1 + 1D transverse Ising model, and so the Z2 symmetry is given by the spin flip, up and down spin flip. And then there is a symmetry is that for example, spin in x direction and spin in minus x direction would be the spin carry a definite Z2 charge. Okay, and then we notice that this operator Z operator flip right spin to left spin, but the Hamiltonian term only contains 2 Z2 together. So we only flip a pair. So therefore, we have a mode 2 conservation of this left right spin, you know. So that's this Z2 conservation of a left number of a left spin is give us a Z2 symmetry. So that is a more standard view. But actually, we can have a Z2 dual symmetry and their corresponding dual charge. To see the dual symmetry, we have to choose a different reference state. You can see here the reference state is that all the spin pointing to the right, that's the reference state. And the spin pointing to the left are the excitation. But to see the dual symmetry, we should take our reference state as a spin up state. So spin up state are, or maybe all spin up or all spin down is our reference states. And then the domain wall between all up and all down is our excitation. And if you look at this this model, we find that this zeta operator don't change up and down spin, so they don't change the domain wall. But the x operator flip one spin, create a pair of a domain wall. So therefore, the domain number of a domain wall also have a Z2 model 2 conservation. And this corresponds to Z2 dual symmetry, and that's it. So clearly, this is really the point of view of order parameter and the disorder parameter. You know, the spins like a charge for correspond to order parameter, order operator, and the domain correspond to disorder operator. So it's really like we want to use the order operator, disorder operator to look at the symmetric system. Okay, and because we have these two separate conservation of some Z2 charge, so we say the combined symmetry or combined conservation is called the categorical symmetry. So that is one way to look at the categorical symmetry. And so when you have two symmetry, you will say, yeah, we have a first Z2, another Z2. We should write this as a Z2 times Z2 dual symmetry. Okay, but we do not write this way really because these two Z2 symmetry are not they are not independent. And to see this, let's look at the following thing: is that a pair of Z2 symmetry charge is created by this Zi Zj. They flip two spin. Oh, they create they flip left or right. So they create two Z2 charge. But we view this Zi Zj as an open string operator with empty bulk. The bulk is empty, but the boundary is just Zi Zj. Okay, so this is called a patch operator. It describes this patch operator. And then a pair of Z2 dual symmetry charge is created by another string operator. Here, this string is more reasonable, where we do the same transformation, but not on all the space, but on the segment. between I and j. We only do the same transformation on the segment. Okay. And in this case, we just flip a segment of a string and create a two-domain wall. Okay. So here I try to see that this a pair of Z2 symmetry charge and a pair of Z2 dual symmetry charge, both are created by open string operators. And their algebra between those open string operators tell us their relation. And we find that these two open string operators have a non-trivial algebra. And that is for example, this if two open string operators kind of straddle each other, they anti-commute. Yeah. So that means these two symmetry is not independent. When you have independent symmetry, these two string operator creating separate independent charge, they would commute. Okay. But here they don't commute. But this kind of non-commuting can be viewed as if you view this different order of operator as a time direction. So like the vertical direction, time direction. So this algebra can be viewed as a closed string operator wrapped around one end of another open string operator. It's kind of like a mutual statistics. So here these two string operators have a pi mutual statistics. So that's describing a way to view why these two symmetry are not independent and have very strange relation, mutual statistic relation. So we we use this V to emphasize this relation. And so with this symmetry, dual symmetry, and we can also see why categorical symmetry can be viewed as a topological order in one higher dimension. Okay, because we can view this the Z2 charge and as a E, the dual charge as M. Okay, and their bound states actually is F. Okay, since E and M actually have non-trivial mutual statistics, their bound state actually is fermion. Okay, and there's also trivial particle we call the 1. So now we have four particle, like 1E MF, and then from their mutual statistic and their statistic, we can see that this one actually form a braid diffusion category described by a Z2 gate theory in one higher dimension. That's in 2+1 dimension. Okay, so this is why this end of a string operator here, the end of a string operator correspond to anions in one higher dimension, and this braiding of a string operator described the mutual statistics of anion. So from a string operator somehow we can construct a topological order in one higher dimension. So that's led to this holographic point of view. So now we can see that we can view this we have Z2 topological order or Z2 gate theory in one higher dimension. Their boundary theory, their boundary will be correspond to a system with Z2 symmetry. Okay, any questions?
We have a question here.
Yeah.
Can you hear me? Can you come closer? Yeah, sorry.
Can you hear me?
Yeah.
How is what you just described different from saying that there's a projective representation of a Z2 cross Z2 symmetry in the system? Is that a different statement?
It's different. Yeah, this is very, very good question. When you have a project, let me see. Yeah, in this case, probably not really a project notation. Yeah, they're kind of different. The project representation of Z2 cross Z2 is described by this anomalous. I don't know. You know, there's another relation. We have Z2 cross Z2 symmetry. There may be mixed anomaly, and then whether this mixed anomaly can be whether this corresponds to the presence of mixed anomaly. That answer is no. Z2 cross Z2 with mixed anomaly and this is Z2 VZ2 are different. They are different symmetry and different categorical symmetry. So actually using categorical symmetry, you can see why this stuff is different from Z2 cross Z2 with a mixed anomaly. They are different. But I will describe that in a moment. Yeah.
Thanks.
So this sounds like a kind of abstract. You know, what do you mean by this statement that this 1 plus 1D Z2 system, Z2 symmetry is described by a topological order in 1 higher dimension? What do you mean by that physically? So it really means the following. And each Z2 symmetric system can be exactly reproduced by a boundary of a Z2 topological order in 1 higher dimension. Okay, so more precisely, I can say the following. For example, when you have a Z2 symmetric system, we can consider a subspace which is a symmetric subspace. I mean, the subspace carries neutral Z2 charge, no Z2 charge. Okay. And the excitation spectrum in this symmetric subhilbert space is identical to the boundary spectrum of topological order in 1 higher dimension. So this is the more precise way to see how close they are related. So certainly we have many different Z2 symmetric system. We also have many different boundary for same topological order in same Z2 topological order. But we try to say that there is a 1-to-1 correspondence. For every Z2 symmetric system, there is a boundary which corresponds to that. And so therefore, every phase transition and etc. and the phase diagram for Z2 symmetric system can be studied via phase diagram of a boundary for topological order and a phase transition and etc. So this is the way we're using this holographic picture. Okay, so let's try to proceed to see how much we can go in this direction. And so let's consider again this Z2 symmetry. Let's consider the gapped ground state. Oh, not gapped, it's just gapped and gapless ground state. And so we know that for the system with Z2 symmetry, we have 3 kind of states. We have Z2 symmetry, we have Z2 symmetric states. We also have Z2 symmetry breaking states. We also have a critical states which describe a transition between the two. So you have 3 different states we are interested in. Okay, it's a 2 gapped, 1 gapless. Okay, but however, we have little problem here. If you're using Z2 symmetry to label those states, we find both the Z2 symmetric states and the critical states are Z2 symmetric. Okay, and then the Z2 symmetry breaking states is gapped that have different symmetry. So we can is that we have 2 different states labeled by the same symmetry breaking, and so that's kind of inconvenient. So here, the one motivation that we want to find a refined way to label those states, but using the categorical symmetry breaking pattern. Okay, so if using categorical symmetry and using their symmetry breaking pattern, we can label those states better. We have better label for those states. And so in this case, the Z2 symmetric states correspond to these dual symmetry breaking states. They are gapped. And the Z2 symmetry breaking states correspond to dual symmetric states, which also gapped. But however, the critical states correspond to the Z2 symmetric and the dual Z2 symmetric states. And when the symmetry and the dual symmetry are both symmetric, both unbroken, the corresponding state must be gapless. And this is result of Michael-Levin. Basically, that's if both order parameter and disorder parameter are 0, then it must be gapless. And also because this special relation between Z2 and dual Z2 symmetry, this mutual statistics, we do not have a state which break both Z2 and dual symmetry. Okay, so this is both broken are not allowed. Okay, so therefore we can see that we can use this categorical symmetry, a different symmetry breaking pattern of categorical symmetry to label these different states, including gapped state and gapless states. And so this actually a way we want to use this categorical symmetry. And this is a more refined labeling, better data. So we can use this data to compute critical property and etc. And so in the following, I'm going to suggest that we can use something so-called condensable algebra mathematical object called condensed algebra to label different categorical symmetry breaking. Okay, and but maybe condensed algebra probably need to be generalized, but you know, at the moment it's a possibility. Yeah. So here just present some kind of a simple result, simple theory. So what is a condensable algebra? Okay, so this really corresponds to the following thing. You can see the boundary have this categorical symmetry called the Z2 and Z2 dual symmetry. And remember this Z2 symmetry, Z2 charge corresponds to the E in the bulk in the Z2 topological order, and the dual symmetry charge corresponds to M in the bulk topological order. Okay. And then we can see that if M condense and E do not condense, and this give us a gapped boundary. So give us a gapped boundary to this topological order. Okay, and that corresponds to a state where this Z2 symmetric and Z2 dual symmetry broken states. If E condense but M do not condense, then it gives us this Z2 symmetry breaking unbroken states. Okay. If nothing condense means only identity operator condense, then this corresponds to the Z2 symmetric gapless boundary. I mean, this Z2 and D2 dual symmetry symmetric gapless boundary. If nothing condense. Okay. So this what condense? So this set of 1 and M, or 1 and E, they are condensable algebra. So they can condense and they can produce a gapped boundary. Okay. And so naively, we can say the condensable algebra is just a set of onions which condense to the boundary. Actually, the more precise definition, very, very complicated. So we're using this naive definition here. I want to say that this 1 and F do not form a condensable algebra because F is a fermion. So fermion cannot condense. Okay. Also, we cannot say this 1 plus E plus M. So this set also not condensable algebra because E and M have a non-trivial mutual statistics. When E and M have non-trivial mutual statistics, they cannot condense together. Okay. So this really says that the so-called condensable algebra are just a collection of bosons with a trivial mutual statistics. So naively, we can view that way. It's a collection of bosons which can condense together. So they are bosons with mutual statistics, trivial mutual statistics also. And also this 1EM is not condensable algebra because they do not close under fusion because E and M bound state is not inside this set. So therefore, condensable algebra is a set of onions which are close under fusion and they are bosons with the trivial mutual statistics. So naively, it's like that. Okay. And so in this case, so we can using this condensed algebra to label. You can see in this case, we can use a condensed different. We have so for this categorical symmetry, for the E2Z2 topological order, we only have a 3 condensed algebra. So these are only 3 condensed algebra we have. You can check. There's no more. Okay. And these are 3 condensed algebra correspond to 3 states, 2 gapped, 1 gapless. And the gapped boundary is called the maximal. So you cannot add more onion to make it a bigger condensed algebra. So usually the maximal condensed algebra give us a gapped boundary. And this one is not maximal. The non-maximal condensed algebra give you gapless boundary. Okay. And so this is really give you a simple example to see how to use a categorical symmetry, means a topological order in 1 higher dimension, under their condensable algebra, to construct the different phase and the phase transition. So that's just an example. So now let's introduce a notion of a so-called unbroken categorical symmetry. Okay, and the unbroken categorical symmetry is following. So given a categorical symmetry, which is topological in one higher dimension M, under the condensed algebra, because the condensed algebra is just a bosons with the trivial mutual statistics, they can condense together. So if we condense those bosons, then we get another topological order, kind of induced topological order we call M/A. Okay. So then this M/A also can have another boundary, but this boundary have a nothing condensed. Okay. Then I want to say that the A condensed boundary for the M correspond to nothing condensed boundary for M/A. The reason is that we already condensed. We already have A condensation when we go from M to A. Then we do not need additional condensation. Okay. And so therefore the A condensed boundary can be viewed as a one condensed boundary of M/A. So M/A correspond, we call M/A unbroken categorical symmetry. So M/A is a categorical symmetry which is not broken. So we have a categorical symmetry broken down from M to M/A. And then then if M/A is trivial, then their boundary can be gapped. Okay, so that really says that if M/A is trivial, then A is a maximum. If A is a maximum, their condensation induced topological is trivial, and then this boundary is gapped. However, if A is not the maximum, then M/A is non-trivial. Then the one condensed boundary of a non-trivial topology must be gapless. Okay, so this describes a symmetry product gaplessness. If there's a non-trivial categorical symmetry, there's a non-trivial unbroken categorical symmetry, then the boundary must be gapless. So this state must be gapless. You know, there's a lot of discussion of this of symmetry product gapless, and this is kind of like a unified way to look at this symmetry product gaplessness. Okay, so now let's using the formula we developed in the moment before to apply to some non-trivial situation. Let's consider Z2 cross Z2 symmetry. Okay, and so we want to obtain is a gapped face, all the gapped face, and but via this via categorical symmetry and via this maximal condensable algebra of a categorical symmetry. Okay, and for the Z2 cross Z2 symmetry, their categorical symmetry actually is a Z2 cross Z2 gate theory in one higher dimension. Remember, Z2 symmetry is a Z2 gate theory in one higher dimension. Here's the Z2 cross Z2 gate theory. And their anions are generated by EA and MA for the first Z2 and EB, MB for the second Z2. Okay. So what is a maximum condensed algebra? For example, we can condense all the M particle. If we condense all the M particle, we actually break the dual symmetry. We break both dual symmetry here, but we do not break the original symmetry. So these are really Z2A, Z2B symmetric states. Or we can condense MA and EB and their combination. In this case, we break the Z2B symmetry, but do not break Z2A symmetry, and etc. So they can see the first four maximum condensed algebra. They are all bosons with a trivial mutual statistics, and their maximum we cannot add. And we get the four of them here correspond to something we are very familiar with. This is 2Z2 symmetry, maybe broken, unbroken, so we have a 4 choice. Then we can also condense another thing, which is the EAEB condense and MAMB condense. In this case, some diagonal Z2 is unbroken. So some combined Z2A, Z2B transformation unbroken, but individually broken. So that's also another familiar symmetry breaking states. But then we have a little bit of surprise here is that we have another maximal condensed algebra, which is EA condense, EAB, sorry, EAMB condense, or MAEB condense, and their generation. And again, they are bosons, they mutually boson also. And this one do not correspond to any symmetry breaking states. It turns out that this one corresponds to the Z2 cross Z2 SPD phase. Yeah. So therefore, in 1+1 dimension, the Z2 cross Z2 symmetry have a non-trivial SPD phase. Okay, and so this is this correspond to that. And so these SPD phases are described by this project rotation of a Z2 cross Z2. Okay, so this really this example tell us that this maximum condensed algebra, their condensation, they describe condensation and describe a breaking of the categorical symmetry. But this kind of condensation not only describe the symmetry breaking states as you expected, but also describe SPD states. Actually, it turns out that in higher dimension, the topological state can be viewed as condensation or spontaneous breaking of a higher symmetry. So therefore, we can expect in higher dimension, this condensed algebra also describe SET states. That means the symmetry, topological order with the symmetry. Okay, and so this is so that's a one aspect of a categorical symmetry breaking, so that we can have a unified way to describe all these symmetry breaking SPD, SET states, just using condensable algebra. Okay.
I have a quick question.
Yeah.
So does your argument work for the non-abelian group? Like if it's a non-abelian anyon, can you apply a similar compensation strategy here?
Yeah, yes, I'm going to do that just here. Yeah, but maybe next slide I will do that. But
yeah.
Just wait a moment. Okay, so here is that there are also non-maximal condensed algebra, and they correspond to gapless states. Okay, and so they have a 10. Actually, it turns out this Z2 cross Z2 gate theory have a 10 non-maximal condensed algebra. So it looks like there's a lot of gapless states. But however, 9 of them, if you're condensing those things, they will the induced topological order, this M/A, actually this Z2 gate theory. Basically, if you're condensing those, you break one of Z2 and only one Z2 survive. So you get just a Z2 gate theory. So 9 different condensed algebra, but give same Z2 gate theory. And so that means that the one condensed boundary of Z2 gate theory, as we already described, is actually is a CFT of Ising model. It's just like C2 symmetry breaking example we just described. So therefore, for this 9 non-maximal condensed algebra, their gapless boundary correspond to this Z2 Ising model. But this one condensed algebra is a condensed algebra is different. They correspond to some central charge equal to 1 CFT. So there's 2 different CFT from this 10 condensable non-maximal condensed algebra, and these 2 different CFT should describe the continuous transition of this 6 gapped phase. and how to put them together is another story. So I will skip that and discuss this non-abelian case. Okay, so our last example actually is apply this picture for this S3 non-abelian group. Okay, and as we expected, this the categorical symmetry for this 1+1 dimensional S3 symmetry is a 2+1 dimensional topological order, which is which simply S3 gauge theory with a gauge charge excitation. Okay, it's kind of like S3 gauge theory. The S3 gauge theory have a lot of anion in it. There's a 2 anion labeled A1, A2. They are really kind of S3 charge. You know, S3 symmetry have a 1-dimensional rotation, irreducible rotation, also have a 2-dimensional irreducible rotation. It's only have 2 irreducible rotation correspond to A1 and A2. And also, as a gauge theory, also have a flux. S3 flux are given by the conjugate class. The S3 group have 2 conjugate class. It's labeled by B and C. Okay, they have a bound state between this charge and the flux. So this B1, B2, C1 are flat charge bound states. So in total, the S3 gate theory have 8 anions. They have 8 anions. And these anions may have this topological spin. If a 0, that means boson. If 1/2 is a fermion, so this one is a fermion. And then if a topological spin is 1/3, these are anions. So you have the 1/3 is anions. Okay. And also they have quantity dimensions. And like a electron spin 1/2 electron have a 2 internal degree freedom, the quantity dimension should be 2. And but here is same thing. Like a 2-dimensional representation have a quantity dimension 2, and there are some other quantum dimension. And they have this fusion rule. So those are really describe a non-abelian topology order. So this Z3 gate theory is really a non-abelian topology order. Okay. So then we want to study their condensed algebra in this non-abelian topology order. And here the calculation of condensed algebra is more complicated. Okay. And so here I want to say the following. Actually, condensed algebra, a moment ago, I just said the condensed algebra is just like a collection of anions. And that saying is not quite precise. The better way to say that the condensed algebra is a composite anion. It's like a direct sum of several different anions. So here we're involving the notion of a direct sum. It's like a spin 1/2 fusion with spin 1/2 became direct sum of spin 0 and spin 1. So you can see that the spin 0, spin 1 have this kind of direct sum, which is a fusion of spin 1/2 and spin 1/2. And here we need to use this kind of notion. So it's more precisely, the condensed algebra should be viewed as a composite anion, and it's a composition of a anion, but the a anion may appear one times or several times. So this a is an integer, positive integer, describing how many times this anion appear in the composite. Okay, so how to compute A is a way to compute the condensed algebra. It's like computation of condensable algebra. And so I will not really go into detail. I just want to say that there's this integer vector AA satisfy many conditions. Okay, but this condition is formulated according to this ST matrix of a bulk topology order. Okay, you can see in the bulk topology order, we can using 2 unitary matrix S and T matrix to characterize the bulk topology order. So this categorical symmetry M is numerically or quantitatively characterized by the bulk topology order. And then from this ST matrix, we can compute this A in some sense. So I won't go into this detail. So there's a lot of condition, and we just find the solution of this all those conditions. So from ST matrix, we can obtain A. That's the point. Okay, what is the results? Then if you do everything, perform this calculation, we find the following condensable algebra. Okay. I think there's 8 of them. Yeah, there's 8 condensed algebra. The first 4 is the maximum, and the second 4 is non-maximal. Okay, and this first 4 is have very simple interpretation. You can see that the first maximum condensed algebra, we're only condensing flux. We do not condensing charge. So therefore, no Z3 is not broken. So this is a Z3 phase. That means Z3 is not broken, have a Z3 symmetry. And here, this one, we condensing A2. Condensing A2, that's A2 is a charge, Z3 charge. That break, this S3 charge. Condensing A2 break S3 down to Z2. So therefore, this kind of maximum condensed will correspond to gap Z2 phase. And etc. This A1, A2 condense everything, so that's Z1 phase. Okay. And so we get this full symmetry breaking phase. Oh, this is kind of expected, no surprise. But still, this is still non-trivial. This means that we don't have any other gapped phase. So all the gapped phase of these three symmetric systems are described by symmetry breaking phase. There's no SPT phase and no SET phase. So that's the results. From condensed algebra, we see that there is no SPT phase for S3 symmetry, and that's indeed true. And for S3 symmetry using group cohomology, we find indeed there is no SPT phase. So that's kind of agree with this group cohomology results. But then the rest of these condensable algebra are really this a non-maximal one. Okay. And the non-maximal one corresponds to the gapless states. So what are those gapless states? What are those gapless states? Okay. So here I want to say that we can compute the gapless states for the non-maximal condensed algebra using an algebraic approach. So there's an algebraic approach to obtain their gapless states, and the critical states. And so what is the algebraic approach is the following. We know that in 1+1 dimension theory, on the space-time torus, the space-time torus are described by a tau. So the shape of a space-time torus are described by a complex parameter called tau. And then the partition function on different shape of a space-time torus are related. So the tau and the tau plus 1 are equal, and the tau and the 1 minus 1 over tau, their corresponding partition function should be equal. So there's called the modular invariance. So the partition function should have this modular invariance. Also, partition function has some kind of analytic structure, or we call the integer non-negative structure. So I will not really go into that. Okay. And so using this modular invariance and this analytic structure, we can algebraically determine what kind of partition function is allowed. And from that, we can determine the gapless states. If you know the partition function for every shape of space-time, you can infer the scaling dimension and the critical and the many critical property just from this shape dependence of a partition function. Okay. However, for the boundary of a topological order, we can do the similar thing, because of when topological order is a gap in the bulk, and the boundary is a cylinder. We have boundary is a space-time cylinder, and the boundary may be gapless. So gapless boundary also have a partition function. Here, the only difference that the boundary partition function is not a single number. Actually, it's a vector. This is because without modifying the boundary, we can insert a word line of onions in the bulk. In the bulk, topological order contains onions. We can insert word line of onion in the middle of bulk without modifying the boundary. Certainly, the boundary is globally modified, not locally modified. And so this gives rise to different sector for boundary. And each sector for boundary gives rise to a different partition function, Zi, which are labeled I is a bulk onion. I label bulk onion. So you have many partition functions labeled by the bulk onion. And then this multi-component partition function is not modular invariant, but the modular covariant. Okay. So they transform under this ST matrix, but this ST matrix happen to be ST matrix characterized bulk topological order. So if you know the bulk topological order ST matrix, then you can determine the modular covariance of a boundary partition function. Then from here, we can obtain what kind of boundary partition function are allowed by this kind of ST matrix, and then from there to algebraically compute the boundary critical property. Yeah, I think I will be finished in maybe in 5 minutes. Yeah, I'll be a little bit over.
Yeah, take your time.
Yeah, and so here is here just a trick, because in 1+1 dimension, we have a pretty complete knowledge of of conformal field theory. So for each conformal field theory, we have their corresponding conformal character. And using those conformal character of conformal field theory, we can construct a boundary partition function. Yeah. So I will not go into detail, and just we can construct the boundary partition function. Okay. And then this and actually from this construction, and we can infer what is condensable algebra they correspond to. Different boundary partition function correspond to different condensable algebra. But once we know this boundary partition function, from this boundary partition function, we can infer this partition function correspond to certain condensable algebra by simply this relation. But I will not explain that, so we just say there's a relation. Okay. So here's the results. And so here what we do is that we consider this condensation, and just one condensed boundary. And one condensed boundary, and for this condensed algebra, what kind of boundary, gapless boundary state do we get? It turns out we can using this so-called 6-5 minimum model, 6-5 minimum model, and their conformal character to construct this boundary partition function. Okay. And this partition function is a one condensed only because this chi0 absolute square. This chi0 absolute square only appear in this first component. So this indicates it's one condensed. So this is one condensed boundary. Okay. And so therefore this one condensed boundary, one condensed gapless CFT is given by this 5-6 model from this algebraic calculation. And so this is really 4-5 state, central charge 4/5. Actually, this one condensed boundary have another CFT. So actually, there's a multiple solutions. And so actually, using this minimum model, 7-6 minimum model, we can construct another one condensed boundary. Again, you can see that this chi0 square only appear in this first component, and that's correspond to, they say there's a one condensed boundary. But from the partition function, and this index actually scaling dimension of a primary field. So we can see that from these two terms, we can see that the scaling dimension is pretty low. So actually these two are relevant operators. In the previous solution, we only have one relevant operator. This one, the scaling dimension more than 1. So 7/5 is bigger than 1, so they are irrelevant. 2/5 is less than 1, so they are relevant. So therefore, this is gapless states with only one relevant direction. And this is the gapless states with two relevant directions. Okay, we just look at this Z0 correspond to this charge neutral sector. So those are symmetric operator with a low scaling dimension. And so you can see that the second partition function is not most stable. They describe a multi-critical point because they have two relevant directions. And the first partition function is more stable. They have only one relevant direction. So that means it describes a stable critical point. The critical point for the stable continuous transition. And this one may describe a critical point for unstable transition, so multi-critical point. So that's how we use this. And similarly, we can do the similar thing. We can have other solutions, like you can using this. You can 6-5 minimum model have another solution. This is a modular covariant partition function. But in this case, you can see that this chi0 square. This chi0 square appear in both one component and A1 component. So because this partition function corresponds to this 1 plus A1 condensed boundary. So that's another gapless boundary, but have this different condensation algebra. And their partition function is this. So there's some condensation. And so this is another critical point. And this critical point only have one relevant operator. It's only relevant operator. So there's critical point. They're not the multi-critical point. Okay. And so then we can using the Ising model. This 4-3 minimum model is Ising model. Construct yet another multi-component partition function. And here you can see that we have chi0 square appear in the 1 and A2. So there's a 1 plus A2 condensed. Okay. So you can see that for every condensed algebra, we can obtain the most stable CFT and their corresponding partition function. And that's describe all different gapless states. So this kind of like is like an algebraic way to obtain all these gapless states. And similarly, this 1 plus B condensed boundary is the same as is also Ising CFT. So I will not discuss this further. So the last point is that so far we just got a collection of a gap state and a collection of gapless states. How to assemble them together to form a global phase diagram? Question is that which gapless states is a critical point between which pair of gapless states, gapless states. Yeah. And actually, so for example, this 1 plus BC is 1 BC is a maximum condensed algebra. 1A, 2B also maximum condensed algebra. But this 1 plus B, remember, look like this 1 plus B is a sub-algebra of these two maximum one. So they are not the maximum one. So it's very natural, this sub-algebra of these two maximum one describe a transition between these two. So therefore, from the algebra sub-algebra relation, we can try to guess what is the global phase diagram. Try to put this propose some kind of RG flow. And so actually we have two we have this RG flow actually this is our proposal from this 1, 2, 3, 4, 5 is this non-maximal CFT we talk about. And so they describe a critical point. And this kind of RG flow would correspond to this phase diagram we obtained numerically. Yeah. But here the thing is that maybe let me describe this thing. Why this S3 to Z1 transition may not exist. Because let's consider this S3 to Z1 transition. S3 is here, totally symmetric. Z1 is here is totally symmetry breaking. And from their condensed algebra, we see that very naturally, they should be connected by these gapless states given by the one condensation, because only one appear in both. So this minimal condensed algebra is correspond to gapless states connecting these two phases. And we also have this S3 to Z2 transition. And their transition is that it looks like they should be connected by 1 plus C. Because you can see 1 plus C is a common in both maximum condensed algebra. The 1 plus C is here, you have also 1 plus C here. But amazingly, for the S3 symmetry, the 1 plus C is not the condensed algebra. If you do the calculation, they are not condensed algebra. So this one is missing. So therefore, if this one is missing, so that means the transition between S3 and Z2 can only go through this one. This is even smaller condensed algebra. Okay, can only go through one. So therefore, we are facing the difficulty that both S3 and Z2 to Z2 and S3 to Z1, they can only be connected by the condensed algebra 1. There's no other choice, And so this is our conclusion that if S3 to Z2 exists and also S3 to Z1 exists, the both transition should be described by the same condensed algebra. That's a one condensed state. And but the S3 to Z2 transition has been shown to describe by one condensed state. Actually, that's a pulse model. This transition is shown to be one condensed CFT. Okay. But S3 to Z1 is not known. So maybe this one do not exist. If they exist, they also describe the same CFT. So this is a way to using this condensed algebra and the topological in higher dimension, try to squeeze out more juice of this symmetry breaking transition. So so this I feel that this is a kind of some kind of algebraic point of view to look at this symmetry breaking transition, or maybe any other transition, or also holographic point of view from topological order in one higher dimension. And using this point of view, we can obtain maybe some new results. Yeah, thank you very much. Yeah, I can't go over time. Yeah.
Yeah, so let's thank Xiao-Gang for the nice talk. So is there any question? So for the audience online, you can speak out directly, and for local people, please come forward to ask questions if you like.
So Xiao-Gang, I had a question. So
Yeah.
now the numerical work that you used in the very beginning to motivate the whole theory, how does this final phase diagram you're showing us here reconcile with the numerical phase diagram, which I have forgotten by now?
Yeah, and so the
Can you connect the two for me, please? I mean, and tell us what you can understand and what you cannot.
okay, so this is the numerical diagram. Yeah. So far, all the theoretical discussion kind of consistent with all three numerical phase diagram.
Oh, okay.
The reason is that this transition is the first order.
Right.
And this transition also first order.
Yeah.
Okay. However, if this transition is a continuous, and if this transition is continuous, the theory also agree.
Yeah. Okay.
What's going on? The point, if this transition is continuous and this transition is continuous, we predict that then this continuous transition will be the same CFT as this one. However, if this continuous transition have different scaling dimension than this one, that will be inconsistent with our theory. But however, but for two different symmetry breaking pattern to have a described as exactly the same CFT is very strange. I can only say that it's very strange. I cannot say it's very impossible. It's very strange. So we try to entertain the possibility that there's no continuous transition between S3 and Z1.
Yeah.
Just like no continuous transition between Z3 and Z2. So actually in the categorical symmetry, these two situations are very similar. If you have a continuous transition this way, we also have continuous transition this way. If you don't have continuous transition for this one, we also don't have continuous transition for this one.
Right.
So that's what we learn from this categorical symmetry. These two transitions are very much, no, sorry, these two transitions is very much related.
Okay, I get it. Thank you.
These two are very related. So from this category, you can see these two similarly unrelated transitions are very related. If they are both first order or they are both continuous, if they are continuous, they should be so there should be same critical point. Yeah, that's what I'm trying to say.
I have a question.
Yeah.
Okay. Yeah. When you talk about the gauge of S3, in the Berg, 2 + 1 dimensional Berg, it's a chiral theory, or it could be like Levin-1 or Kilaev's discrete model is a double.
In this particular case, it's a non-chiral, but however, it has gapped boundary. It has gap boundary. But here we don't care is whether chiral or non-chiral. We do care whether it has a gap boundary or not. It has gap boundary means it has a gapped face. So actually, I skip that. And so there's another example. For example, this S3 with a anomalous symmetry. The S3 symmetry can be anomalous in one dimension. So if you have this for an anomalous S3 symmetry, we can also obtain their gap state and gapless states. In this case, the S3 anomalous, the bulk is a S3 diagram written theory. This theory is a chiral, but have a gapped boundary.
Okay.
But the S3 symmetry is non-chiral, also have a gap boundary. But for us, we just care it have a gap boundary, so they have a gapped face. They have a gapped boundary face. Yeah.
Okay. But we know that the excitation spectrum of the Berg chiral or double gauge series, they have different spectrum.
Yeah, they have different
Therefore,
spectrum.
their
Yeah.
condensable algebra, the choice may be different, right?
Exactly. So because this for anomalous symmetry, the bulk is a Algebraic theory. They have different ST matrix. So therefore, we get different condensed algebra. So those are condensed algebra for the S3 with the first anomaly or the second anomaly. You can see they're all different. You can see different anomaly give a different condensed algebra, and as a result, you have different gapless states. The gapless states also different. In particular, there's one interesting one, and we have a stable gapless gap the face. I think this one is a gap the face. For the S3 symmetry with this second anomaly, it have a gapless face. Describe this kind of CFT. So right mover is E8, and the left mover is a SO9 level 2 Categorical algebra. And so again, you can get but there's no anomalous dimension, no relevant operator. So this one is a gapless face. Yeah.
Okay, so your general result should be applicable to both cases. I mean,
yeah, exactly. So you can see that our calculation only depend on ST matrix, do not depend on symmetry. So whenever you have a bulk topological order, you can do this calculation. So that's what I mean by the generalized or the unified description. You know, symmetry or non-symmetry, they all described by bulk topological order with ST matrix. Once you have ST matrix, you can go through the algebraic calculation between the gap and the gapless boundary. Yeah, so that's basically my point here.
Okay, thank you.
Yeah, there's a question from Galton. Please speak.
So I had a question about if the group is continuous instead of discrete. For example, in 1 plus 1D, if I take, like, there's no U1 symmetry breaking because of Merman-Wagner theorem. Is this like related to the fact that there is no deconfined phase in 2 plus 1D?
Yeah, and you have a very good question, and but I don't have an answer. And the thing that this holographic point of view only works for finite symmetry. Okay, because we have continuous symmetry, the bulk gauge theory would have a continuous group. The gauge theory with continuous group is not gapped. It can be gapless. So there's so what I described here do not directly apply. So it's an open question. So we are dying to find a way to generalize this point of view to continuous symmetry. They might be non-trivial, as just exactly as you said. For continuous symmetry, we have this ghost mode, you know, have all this kind of new twist, a new feature from continuous symmetry. And this holographic point of view should capture those new features. And how that happens, you know, at the moment, I don't know. But it will be a lot of fun, you know, how to generalize this general picture for continuous group. Yeah, so this is our unified description only apply for finite symmetry. For continuous symmetry, we have trouble at the moment.
Thanks.
Is there any other question here or online? Yeah, if there's no question, let's thank for Professor Xiao-Gang Wen for the nice talk. Yeah, thank you very much.
Thank you for the invitation.
Yeah, so we will upload the video onto YouTube soon.
Okay. Yeah, thank you.
Yeah, thank you. So everyone, bye.
Bye-bye.